Hello, dear aspirants, dear students, dear candidates, ladies and gentlemen. Special greetings to every one of you. Wherever you're watching, I'm God will, Yakub. Today I will take you through chemistry, and we'll be doing a very important topic in chemistry. I'm going to make it very easy to understand, I mean simple for you to understand as we walk through the journey of chemical equilibrium. So we're going to be discussing today's class on this topic, chemical equilibrium. Okay. All right, and the first thing that we're going to discuss on chemical equilibrium is an equilibrium equation, an equilibrium reaction. So what does it mean? The 150 questions that beg for an answer is, what is an equilibrium reaction? Alright guys, so without wasting of time, we're going to start with a reversible. I'll explain what we mean by equilibrium. But before then, let's look at a reversible equation, okay? So, because equilibrium is only attained by reversible equations, we're going to discuss what we mean by reversible equations. Then we'll discuss a type of equilibrium. So let's get started. What is a reversible equation? When we have a reversible equation, the sign of a reversible equation is this, which indicates what? The forward and the backward reaction taking place at the same time. So a reversible equation is that equation in which, as the reactants combine to form products in the forward reaction, the products also react to form the reactants in the reverse reaction. So what does it mean? A reversible equation has two reactions taking place. We have the forward reaction and the reverse reaction. We'll take a very good example. The symbols not, the letters not being the usual symbol of the element, okay? I'll use this A plus B in a reversible chemical reaction to give us C plus Z. Now, from here, from your knowledge in chemistry, A and B here represent what? The reactants, right? These are the reactants because they are the ones that will form the product, right? Then here we have the product. Now, what makes this equation or this reaction a reversible reaction is the fact that as these reactants, they are forming products. At the same time, the products are forming reactants. Okay? Now, we are talking about equilibrium. Okay? Meaning that, in fact, at a state of equilibrium, the rate at which the reactants form products is the same as the rate at which the product form reactants. So when observing the equations, it's just as though nothing is happening because reactants are forming product and products are forming back reactants. So we do not have more of reactants at any point in time or more of product at any point in time, we talk of equilibra. I want to believe that that is well understood. So that's a reversible equation. A reaction. A reversible reaction is a reaction in which as the reactants combine to form products, the products in turn will combine or react also to form reactants. Yeah. So uh, we have the forward reaction and then we have the backward reaction. So that said and well understood, I'm going to take you through the characteristics of equilibrium. And the equilibrium we'll talk about here is the dynamic equilibrium. Okay. So what are the characteristics of equilibrium? Uh, when can we say that a reaction has arrived equilibrium, or when can we say that the state of equilibrium has been attained by a chemical reaction? It's going to be short and simple, guys. Rate of reaction, I explained it already and I'm explaining it again. At equilibrium, the rate of the forward reaction is the same as the rate of the backward or the reverse reaction. It means that the rate at which the reactants form their products is equal to the rate at which the products form back the reactants. So that is it. At equilibrium, rate of forward reaction is equal to the rate of backward reaction. Simple and easy. Okay, now look at some key characteristics of equilibrium reactions, right? Number one, such reactions occur in a closed system. Equilibrium reactions occur in a closed system. Then macroscopic properties remain constant. When we talk of macroscopic properties, we refer to properties like what? The concentration. Concentration does not change. Concentration remains the same. The concentration of concentration of reactants don't change. Concentration of product don't change. When we talk of macroscopic properties, the colors don't also change. Pressure doesn't change. The reaction will continue at molecular level. Then we talk of the dynamic nature. The reaction does not stop. Okay. Now, even though normally in a normal chemical reaction, let me show you what happened. If this was not a reversible reaction, we'll have just one arrow here. Okay. So now the reactants form their products. The objective of this reaction is that the reactant at the end is a product, right? So let the reactants form the product. So understanding this in chemistry means that the concentration of the reactants should reduce. Or in short, the amount of reactants should reduce and form products so that the product will now increase. So as the reaction is going on, reactants are forming product. The reactants are reducing and products are increasing. This is a normal reaction in chemistry. But now, guys, in a reversible reaction, look, reactants are forming product and products are forming reactants. But now the concentration is not more reducing and this one is increasing. It's constant. The reaction is not taking place. That's one thing I'm trying to explain now for you to understand here. The reaction continues, but as reactant form product form reactants. So the same amount, reactants seem as if it's not increasing, it's not decreasing. It's not decreasing. Same for product, not increasing, not decreasing. But the reaction there's a dynamic nature that the reaction continues taking place. That is it. So equilibrium also can be reached from either direction. So either starting from the reactant or from the product. So after understanding that, it's now important we talk on the type of equilibrium, right? Type of equilibra. Okay, we're soon coming here. Let's look at the type of equilibra. Like I always say, if you have any question, you can use the comment section, and then you ask your worries, you ask your question, I'll be in the comment. I'll answer to your questions. Yeah. So, uh, what are the types of equilibra that you know? Some student will be able to at least cite maybe 2 in the comments before the lecturer is getting there. But simple for short, we can start from physical equilibrium. Okay, physical equilibrium. I will give you type of equilibrium. Explain that particular type of equilibrium. So physical equilibrium first. Physical equilibrium. When we talk about physical equilibriums, physical equilibrium, it occurs when the substance changes their physical state. That means, let me take an example. Let me take an example of bromine. All right, you know very well that we have bromine can take 2 states, both the liquid and the gaseous state of matter. So now watch closely. From bromine BrO2 in the liquid state changing to BrO2 in the gaseous state. That's liquid bromine that is being converted in a chemical reaction to gaseous bromine. What has happened here? This reaction attains equilibrium, meaning that then this equilibrium here will be described as physical equilibrium. Why? Because the substance that is involved has changed the state, has changed the physical state from liquid to gas, or otherwise any other change of state of matter. So then we will talk of what physical equilibrium. All right. Now, the second type of equilibrium now is a chemical equilibrium. When we come to chemical equilibrium, we'll look at it in 2 ways. So other chemical equilibrium, we'll talk about it in A and B, right? We'll talk about the homogeneous equilibrium and the heterogeneous equilibrium. Okay, yes. So looking at the phases. So let's start with the homogeneous. The homogeneous chemical equilibrium. So the homogeneous chemical equilibrium is this actually occurs when the substances they occupy the same phase. They occupy the same phase. Let's take maybe the reaction between hydrogen and iodine to form what we may call hydrogen iodide, right? So we have discussed. I'll clean here and then. Yes, because we have already looked at what we call an irreversible equation. So this can go up. All right. So ladies and gentlemen, watch here. We have discussed what physical and chemical equilibrium. And what has the lecturer said? These are the 2. Now, under chemical here, the state of matter, the state here will change. I use an example of bromine. Now, with chemical equilibrium, it can be homogeneous. It can also be heterogeneous. It can also be heterogeneous, right? Let's look at homogeneous chemical equilibrium. I'm going to take an example with the formation of hydrogen iodide, right? Okay, H2, hydrogen is the gaseous state, plus iodine, gas, in a reversible chemical equation. In a reversible chemical reaction, to give us hydrogen iodide, balancing the equation, you have to in the gaseous form. So when you look at it, you notice that all the components, meaning the reactants and the product, all of them are in the same phase. Which phase? They are in the gaseous phase, right? Gas, gas, gas. So the reactants here are hydrogen and iodine. the product is hydrogen iodide. Okay, so this is purely what we describe as, homogeneous equilibrium. All right, for all those who are watching me on screen, I'm Godwill Yakum. I want to be sure that you are seeing what I'm doing on screen. All right. So we are going to continue from there. Okay. Please let me know in the comments if you that maybe you can't see clearly. That's what I've been trying to do for the past few seconds to see if to be sure that you have the screen so bright. All right. Okay, so that's very perfect now. I can see that it is bright, so you can see me clearly. You can also see the board clearly. Now we're going to proceed. Proceeding, we're going to now look at the second type of chemical equilibra, which will be the heterogeneous equilibra. So here is just simple, and it is to the effect that the components now they are going to be in different phases. So let's take an example of calcium carbonate. Okay. Let me put it here. Calcium carbonate. Yes. In a reversible chemical reaction, calcium oxide and carbon dioxide gas. Calcium oxide solid, calcium carbonate solid. So when you look clearly, you are going to notice that the substances are in different phases. You have the solid, state, and gas. So the substances are in different phases. The components are in different phases. So that's it. It is important to note that it is important to know that solids and liquid are not included in equilibrium expressions. All right. So solids and liquid are not included in equilibrium expression. Please just note that. Now we will go to a very important part of our lesson, which will be the equilibrium law and the equilibrium expression, KC, okay, and the equilibrium law. So that is where we are right now. All right. So what do we mean by equilibrium law? We're going to state the law and then we interpret it. We're going to look at the expression for the equilibrium constant. So first thing first, the equilibrium law. The equilibrium law states that if a reversible reaction is allowed to reach equilibrium at a particular temperature, then the molar concentration of the reactants, each raised to the power of its coefficient in a chemical equation, is a constant known as the equilibrium constant. That is the equilibrium law. I will come again. The equilibrium law states clearly that if a reversible reaction is allowed to reach equilibrium at a particular temperature, then the product of the molar concentration of the reactants, each raised to the power of its coefficient in the chemical equation, is a constant known as the equilibrium constant. Now let's talk about the equilibrium constant. We are considering this equation. We are considering the equation A plus B giving us C and Z. But now, in consideration of this, we also consider the coefficient of each of them in a balanced chemical equation. So the coefficient of A being small a, B and then Ct, just like that. Then the equilibrium constant Kc is the concentration of the products raised to its power times the concentration of this other product raised to its power. If there are 5 products, you will put them like that, divided by the concentration of the reactants raised to its power, concentration of the reactant raised to its power, just like that. So you can see that A and B are your reactants here, C and Z are your products here. So for short, how do you memorize this? It tells you that Kc is what? The concentration of products raised to the power of the product. The power is what? The coefficient. So let me put coefficient here, raised to the power of the coefficient of the products, divided by what? The concentration of the reactants raised to the power of their coefficient, the coefficient of what? The reactant. That is just it. So when we put in square bracket like this, it means the concentration. We are putting in square bracket to simply tell you that we are talking about what? The concentration. So in chemistry, sometimes let me not say sometimes, most often, because this is always there in your exam. Now, well, we can ask you a question of write the expression for Kc. It is going to be simple. You will do this. And this one is just for you to easily remember. This is the expression for Kc. Are we together? All right. That's said and well understood. We will proceed from there. We will proceed now to look at the interpretation of Kc. All right. The camera is. We're going to look at the interpretation of Kc. All right. Value greater than 1, less than 1, or or approximately equal to 1. So the value of Kc has different interpretation. So with those three different kind of value for Kc, we have three interpretations for Kc. So now, if Kc is far greater than 1, right? Can I clean? I'll clean here. Okay, now watch closely. If Kc is bigger than 1, far bigger than 1, what does it mean? It means the numerator is very big, bigger than the denominator by a great value, right? It means the quotient is big. So what will it mean? It will tell you that the concentration of the product is far much greater than the concentration of the reactant. So if Kc is far greater than 1, it means that the product is favored. We will simply be trying to tell you that what the reaction favors the product, meaning that what the more of the products are going to be formed. Okay, now the next, Kc can now be far less than 1, and the reverse happen. The reactant is favored. Okay, so if Kc is far less than 1, the reactant is favored. Now Kc can be equal to 1, and sometimes can be approximately equal to 1, not exactly 1, but a value very close to 1, approximately 1. So in this, it means both the reactants and the product are present in almost equal amount. That's the interpretation of the value for Kc. So Kc, which is the equilibrium constant, can have a value far greater than 1, far less than 1, or approximately equal to 1. Then now, for gaseous equilibra, okay, we consider the pressure, and then we have now the Kp. All right, for gaseous equilibra, Kp is, the expression for Kp is not different from the expression of Kc, but Kc has to do with what? The concentrations. We use the concentrations of the product and the concentrations of the reactants. But now, for Kp, all right, we use the partial pressure. All right, so this is the partial pressure of C, partial pressure of Z. We still raise them to the same power. So it's the partial pressure of what? The products raised to the power of their coefficient divided by the partial pressure of the reactants raised to the power of their coefficient. So that is it. Now, but okay, very soon we'll talk about the relationship between Kc and Kp, right? Yes. So, but that is what you have to understand for now. The expression for Kc, the expression for Kp. Good. Kp is for gaseous equilibrium. Now, what relationship exists between Kc and Kp? Kp is the same as Kc times RT to the power delta n. Let me explain. Kp here is equal to Kc, which is the equilibrium constant, right? Kc, right? Times RT. What does R stand for? R stands for the gas constant. You know the ideal gas constant, right? Yes. Most when the other components are in their SI units, then use Kc. Use the gas constant R to be 8.3. Okay. Yes, but it now has different values in different units. This is for the SI unit. Then T represent the temperature, and it should be in Kelvin, right? right? Because the SI unit for temperature is Kelvin. Now, what about N stands for the number of mole, but we're talking about delta N. Delta N simply means change in N. Delta N means change in the number of moles. So it means that moles of the gaseous product minus the moles of the gaseous reactants. All right. So once to talk on the reaction quotient, the expression also remains the same. QC, you can just come and replace QC here. It will be what? The same expression like this. But I mentioned something here. QC is identical to KC, but uses initial concentration. The concentration here, we use the initial concentration of the product and the initial concentration of the reactant. So that is how we get the reaction quotient for QC. We can predict it. We can predict the value for QC. QC can predict direction, which is the most important thing. QC can predict. Now let's take a situation where K is bigger than. Let me write it for you. If QC is far bigger than KC, also it can be far less than, and then it can be approximate. So if QC is far greater than KC, it means that there's going to be a shift. If QC is bigger than KC, there will be a shift to the left. On the left we have the reactant, and on the right we have the product in a chemical reaction. So there's a shift towards the reactants. And if QC is less than KC, the shift to the right. I mean, but now if they are almost the same or actually the same, it tells you that the system is at equilibrium. Now we'll be talking on a very important principle in chemistry, which is known as the Chatelier's principle. Yes, the Chatelier's principle. So we're going to talk on the Chatelier's principle. Le Chatelier's principle, you can see it here on the board, and I read. Le Chatelier's principle simply states that if a system is in equilibrium and one of the external factors is changed, the equilibrium will shift so as to annul the effect of the change. I'll come again. Le Chatelier's principle states that if a system is in equilibrium and one of the external factors is changed, the equilibrium will shift so as to annul the effect of the change. That is the statement of Le Chatelier's principle. Now, it means that if a system is at equilibrium and then the system is disturbed by a factor, when a factor is changed, it disturbs the equilibrium situation. And what happens is that then to change, to annul, cancel, or to oppose the effect of change. So, now, it can be affected when concentration changes, when pressure, volume, or temperature. These are the various external factors that can affect or that can change or disturb equilibrium, and the equilibrium will now shift to cancel the effect. So we'll start with the first being, you know, yeah, we'll start with the first being uh, the temperature. Yeah. So the temperature changes. If the temperature changes from the reactants to the products, uh, we are going to look at it in two ways. If the temperature changes, if the temperature of the reactants is less than the temperature of the product, it means that temperature has increased. When temperature increases in the chemical reaction, it means that reaction is an exothermic reaction. Okay, so in an exothermic reaction, the temperature will the temperature increase, and when temperature increases, it will be to the left, and then to cancel the effect, and temperature decreases, there will be a shift to the right. That is it. Because temperature decreases, meaning that the temperature here is greater than the temperature for the product, so that's an endothermic reaction, and there will be a shift to the right. A minute. Okay, so we'll quickly go through the factors that can affect the value for case. Uh, in fact, factors that can affect equilibrium causing a shift according to the Chatterjee's principle. So let's talk about concentration. Right? When concentration, let's say we increase the concentration of the reactants. If reactants increase, the reactants here, you increase their concentration, equilibrium will shift to the left. And if you increase the concentration of the product, equilibrium will shift to the right. That one is clear. Now pressure. Pressure is only for gaseous equilibrium, right? Only for gaseous component. So now if pressure of if the pressure is increased, right? Now the shift, if we increase the pressure, the shift will be to the side with the fewer gas moles. Then if the pressure is decreased, the shift will be to the side of the side with more gas moles. Yes. Important note. Volume. Talk about volume. Volume changes can increase or decrease. If volume decreases, the shift will be to the side with fewer gas moles, and if it increases, it will be to the side with more gas moles. So the change in volume and that of pressure are the change. You see, temperature, I already explained temperature. Uh, yes. So the last thing now for today's class is what? The solubility product. We're going to look at the solubility product, and then that will bring us to the end of today's session. Okay, so simple and for short, we have the solubility product KSP equal to all right, good. We're going to consider an equation ax by in a solid state in a reversible equation. Products, we have x a plus a cube plus y b minus a cube. All right, so this is a solubility equation, as you can see, and of course understand from there. So from here we have a solubility expression KSP. It will be a ion, this raised to the power x, then times b, that's minus this raised to the power y. So that is it. And of course this is where our class takes an n, right? So we're going to take an n here at this juncture. We have been talking on what? Chemical equilibrium. And I said I'll go straight to those things that you need to understand. And so we have gone through, we started by looking at reversible chemical reactions. We exhausted that. We discussed the equilibrium law and the equilibrium constants. Yes, we used concentrations and partial pressure. We did the Chatelier's principle and the factors that can affect the equilibrium. Yes, and so now we end here to see again in our next class.